Hello children. In our previous 3 videos of this chapter, pairs of linear equations, we just saw 3 pairs. We saw 3 pairs and we also saw that in each case, the graphical representation of those pairs of linear equations were different. Of course, if you haven't watched those videos, it's still okay. I have pasted the images of the graphs we had done from those videos here. You may just follow this, and later on when you find time you can have a look at those 3 videos. Now, what were the examples? The first one we saw was this one, where the pairs of linear equations intersected and it gave rise to a unique solution. You had found a unique solution. And the second example we saw was that the two pairs, that pair of linear equation which we saw had coincided, like this one here. They had coincided. This is an image from that video, of course. They coincided, and hence we had found that they were infinite solutions. That is, both the lines were overlapping. So every point on these lines was a solution. So they are infinite solutions. And the third case we saw was this one. This one where the lines were parallel. That is, they never met. If the parallel lines don't meet, right? So there was no solution. There was no solution. Now let us explore this one by one and see why we got what we got. Fine. So let us talk about this one first. The case where the lines coincided, where we got infinite solutions. If you have a look at the equations closely, which gave rise to these lines. Let me rewrite the equations for you here clearly. The first one was 3x minus 5y is equal to minus 6, and the second one was minus 6x plus 10y equal to 12. These were the two equations which we had worked upon, and in order to find the coordinates, we had actually reduced it to the y is equal to ax plus b form, isn't it? We wanted to find the coordinates in order to plot the graph. So we made it in this form, and only then we observed that the equations were the same. They were not different at all. Both of them were the same. And then we plotted the graph. Of course, you could plot only one line because it's just one. It boils down to one equation, isn't it? So, and just to show you that there were two lines, we are using different colors here. Now, if you observe these two equations carefully, maybe we could have found out that they are going to be coinciding lines even before arriving at this particular format. Why? How we could have found out? If you observe keenly, 3 has been multiplied by minus 2 and minus 6 has been arrived at. Same way, minus 5 has been multiplied by minus 2 and you got 10y. Right? Minus 5y has been multiplied by minus 2. And same way, the constant term also has been multiplied by the same quantity minus 2 and 12 has been arrived at. So it's the same equation. The one is dependent on the other equation. Now if I write this in the general form, how can you write it in the general form? I am giving a common term for this, the coefficient of x. Let it be a1. This is the first equation. So I am giving a1 b1y is equal to c1, and second equation, let's say it's called a2x plus b2y is equal to c2. So in our special case, we found that this equation 3x minus 5y is equal to minus 6, both the LHS and the RHS has been multiplied by minus 2, right? But so in the general case, let us say that A2 has been obtained. A2 has been obtained by multiplying A1. A2 is equal to some k into A1. In this case, its k was minus 2. Here it was minus 2. So we are just generalizing this. A2 is equal to k into A1 and B2 was obtained by multiplying B1 into the same k and C2 by k into C1. So this is, we have just generalized what we discovered here. Fine. So you can in other terms write this as the ratio of the two coefficients was found to be some constant and the ratio of the two coefficients of y was also found to be the same constant. B2 by B1 was also k and C2 by C1 was also k. So again I am saying in our case it was minus 2. We are just trying to generalize so that we arrive at a place where we can identify that the equations are one and the same without having to come to this format or without having to plot the graph, find the coordinates, etc. So this is what has happened here. The LHS of this equation, this is your LHS and the RHS has been multiplied by the same constant, isn't it? So in such cases, when the LHS and RHS are multiplied by the same constant, we get coincident lines, overlapping lines. So in our case, in the general case, this has been a1x plus b1y has also been multiplied by k and c1 has also been multiplied by k to give rise to or to find your other equation a2x plus b2y is equal to c2, isn't it? So now we have arrived at a general rule wherein we can identify such equations. The general rule is a1 by a2 is equal to b1 by b2 is equal to c1 by c2, where a1, a2, b1, b2 are coefficients of x and y respectively and c1, c2 are the constant terms. So if you find that in any two equations this is your case, if you find if this is the case, then you may rightly conclude that they would form coincident lines. What has happened here? That both the LHS and the RHS, have been consistently multiplied by the same k, isn't it? By the same constant, by some constant, but the same constant. That is why they are the lines which represent these equations are coinciding. They are coincident and the equations themselves are dependent on one another, right? So this is our first case. We have arrived at a general rule. Now let us see what happens in the case of the parallel lines, the equations which form parallel lines. This is our second one here where we found no solution. So let me rewrite these equations also for you. First one was x plus 2y is equal to 8 and the second one in red here was x plus 2y is equal to 1. What do we observe here? Here also something has gone, something is similar but something is not similar. So what is similar? The LHS is similar, right? This is the LHS. It's similar. RHS is not. What has happened to the LHS? It's been multiplied by 1. 2 has been multiplied by 1. Of course, I could have shown you a different example where it has been multiplied by 4 or multiplied by 5 or multiplied by k, whatever. But I have just taken the simple case of having multiplied by 1. You can try out the rest as a trial for practice. But if you observe keenly, only the LHS has been multiplied. The RHS has not been multiplied by the same constant which has been multiplied in the LHS. The RHS, there seems to be no relation between those two terms. So the multiplication has happened, but it has not been consistent. It has not been consistent. It has been inconsistent. This is why we are calling this system, this pair of linear equations to be to have inconsistent solution or inconsistent pair of linear equations, because and because they were inconsistent, of course, not multiplied. Not what is consistency? Well behaved. Suppose you do an experiment in physics, and once you get a reading below 10, and the next time you get a reading somewhere above 100, it's total inconsistency, right? Somewhere you have gone really wrong. So this, in this case of parallel lines, in this case of arriving at parallel lines after plotting the graph of two equations where they do not meet at all, where there is no solution, we call this an inconsistent system of linear equations, right? So this is given rise to no solution. I hope you have understood the difference between both clearly, but maybe your mind, you would be thinking, why at all parallel lines? Why not anything else? Why parallel lines? Of course, it's a very good question if you think of it. We will deal with it separately in another video. Why only parallel lines? We'll deal with that issue. Now I just want to discuss about the third one, the third case where you find a unique solution. So let's do that. Yeah. So in this case, what were the equations? We had formed the equations. One was x plus y is equal to 10, and your second equation was x minus y is equal to 4. So same way we had worked out upon these equations, we had found coordinates, we had plotted the points, and we found that the lines intersected. The lines intersected. We found that the lines were in different angles, as in contrary to the previous two examples where you saw that both were in the same angle. The angles were the same, just that one was coincident and one was parallel, but the angles were the same. Here they were in different angles. So only if they are in different angles you can arrive at a unique solution, and this is the case which we see often in real life also. If you are given information about various real life scenario, the information should be in such a way that they are not dependent on one another. Only then you can arrive at a solution. What is the use of giving dependent equations? You will not arrive at any solution. Here you arrived at one particular point, which would satisfy both these equations. That particular point has satisfied both the equations. So you have concluded that this particular point, the x coordinate is the solution for the number of girls in the x-axis, and the y-coordinate is a solution for the number of boys, which is represented by the y-axis. So here, if you see the general form, a1x plus b1y is equal to c1, a2x plus b2y is equal to c2, you would have observed that there was no relationship between the ratios. A1 by A2 would not be equal to B1 by B2, and this also would not be equal to C1 by C2. They are independent of one another, and that is why the lines representing those two equations had different angles, and that is why you had a unique solution. This is also in contrary to the other two, where this, for the first one, coincident lines, you had this, and whereas for the these two lines which were parallel, you found that this has been multiplied by 1 in the LHS but not in the RHS. So if you write it in the general form again, A1 by A2 was equal to B1 by B2, but they were not equal to C1 by C2. The constant term was different. So it's been consistently multiplied in the LHS by the same quantity, but not in the right hand side. Only the LHS has been multiplied. The right hand side has not been multiplied by the same quantity. So there is inconsistency in the multiplication itself. So this is a inconsistent system of linear equations, whereas the other two were consistent system of linear equations. Right? I hope you understood what I was trying to say. By looking at the equations, you will be able to conclude whether the graphical representation of them will be coincident or parallel or will provide a unique solution by looking at the ratios of their coefficients and constants. Thank you for listening.